Good morning, corn breeders, research scientists, wherever you are in the world, whether you're harvesting or planting right now, since it's either summer or winter, depending on where you are. I just want to reach out to you and say you got one of the greatest jobs in the world, 99.9% failure rate. They'll still build a monument to you if you find a couple really nice cultivars. Now, having said that, this is David Benson with Cornhusker Hybrids LLC in Lincoln, Nebraska, where our mantra and trademark is success starts with the seed. No truer words have ever been spoken. Entire civilizations have rose and fallen depending on the quality of their seeds. So today we're going to get into something really exciting to me, which is genetic variance. And we're going to do what we've been doing, which is work with this genetic gain equation. And we're going to work in that phenotypic standard deviation on the bottom and the last variable in there called sigma squared G. We're going to talk about genetic variance. It's what you do, all the work you do for, and how you exploit it and how you use it. What is it in very simplistic terms? I'm even going to use a little bit right out of Falconer. Maybe some of you most recent graduates don't know what Falconer is, but it used to be the Bible on quantitative genetics, at least when I went to college. So what is genetic variance? Well, it is the variance of breeding values. That's what the book will tell you. Well, what's a breeding value? It's the value of an individual by the average of the mean of his progeny. That's what a breeding value is. So when you look at a test and you have your final test of you've had 10 environments, 2 replications, 40 genotypes, and you're looking at the values in a means table, or you're looking at a regression line through it and you're figuring deviations from the mean, those deviations from that mean actually are the breeding value of that individual in that experiment, plus or minus, because that's how you'd measure it. Now, I believe that's right, and we'll check the actual physical Falconer determinant, but parents pass genes, not genotypes. Remember that. And we're really going to focus in on additive genetic variance because that is the variance that really drives the response to selection. It is the variance that is exploitable in breeding programs. And the more you can cut out all the noise, environmental, we've got this little equation. You've got, of course, we haven't talked about year effects, but you've got air variance, you've got genotype by environment interaction, and then you have genotypic interactions. You cut all the other noise out of your data and you can get to the additive genetic variance, which is the narrow sense heritability, which are alleles that assort additively and independently of one another in a breeding program. They're the ones you go after. So, I'm going to just read some of this right out of the book just to make sure that I get the point across, because this is a big point. Okay, a breeding value, according to Falconer, page 117, is the value of an individual judged by the mean value of its progeny. Breeding value, therefore, can be measured. Okay? That is what a breeding value is in simplistic genetic terms. What is additive variance? Well, if you go to, again, into Falconer, page 128 in the book I have, which is like the Bible. I probably read it 50 times, still probably don't know 5% of it, but I keep trying. The additive variance, which is the variance of breeding values, is the important component since it is the chief cause of the degree of resemblance between relatives in one of the 3 basic genetic phenomena. What is the degree of resemblance between relatives? I've got a son-in-law that's 6'5" and a strawberry blonde, and you should see his son. He looks exactly like him. So my wife has pictures of 2 generations before her in one side of the family, and you can pick out the girls today that look like those photos. Okay, that's what we're talking about. It is the chief cause of resemblance between relatives, and therefore the chief determinant of the observable genetic properties of any population, and importantly, the response to the population to selection. It is like the Taj Mahal. It is what you're after. That is the reason that sigma squared A is in the top of this equation. And you can reduce this really quickly to just Kc sigma squared A over sigma pH by Y, and you can cut all of this out of here, or you can further expand the the phenotypic standard deviation to include things like other sources of data that we have today from drones, from artificial intelligence, from robots. Are those things, all of that stuff out there, increasing the rate of genetic gain or just sucking up resources? Someone probably needs to figure that out. So that's really what I wanted to talk to you about today. I wanted to set the table for understanding what genetic gain actually is, and also as we move forward to interpret how you measure genetic gain and how you quantify genetic gain and how you exploit genetic gain. So this is David Benson with Cornhusker Hybrids LLC in Lincoln, Nebraska. I want to emphasize to you, if I was a professor, I'd go sigma squared A, additive genetic variance, the variance of breeding values, determines the degree of resemblance between relatives. And these are intra-locus interactions, not inter-locus interactions, such as dominance, overdominance, epistasis, or anything else you can think of. And when you look at delta G, it's sigma squared A, sigma squared D, sigma squared AA, sigma squared DD, sigma squared A by D, and everything else is in there. And we want to get that down as much as we can to additive, because we can exploit that, because relatives, parents don't pass on their genotypes. They do what? They pass genes. It's a basis of plant breeding. So today I'm going to close out. I hope you're having a great day, whether you're planting or harvesting, and where you are in your growing cycle, because this is the greatest job in the world. We are privileged to be able to do it, and go out and enjoy your work. Have a great day, and we'll talk about how to measure genetic gain next week.